Hello people, I'm Bharat Acharya. Welcome to our course on the introduction of 8051 microcontroller. Here, I'm going to give you a brief idea as to what is a microcontroller, what are the features of 8051, its processor, its memory, its I/O, and make you curious enough to start learning 8051. The idea of this course is to put you on the right, give you the right platform and put you on track to start learning 8051. It's big, but it's extremely interesting. All of 8050 on the instructions, programming, real-world interfaces, its interrupts and serial communication, all of those are so exciting to learn, but that's much ahead. Before you go there, you need the right platform, the right introduction for it. That's what is the purpose of this course. I have been teaching this subject since 21 years. I'm going to put all my experience into it and try to make it as exciting and interesting for you as I can. Okay, hope you enjoy learning it. Let's start. Now, what's the purpose of a microcontroller? A microcontroller or a microprocessor is used to execute programs. Are we clear? That's all it does. It executes programs. Everything else that you see it's doing is a result of an execution of a program. For a simple example, the wireless Bluetooth music system or earphones, whatever you use, they also have microcontrollers inside. What does it do? From a layman's point of view, what does it do? It plays your song. From an engineer's point of view, what does it do? It runs the audio playback program, a program that takes the song as the data, processes it, makes audio out of it so that you can hear it. When you learn 8051 completely, you'll know how all of this happens. Further, it also does a program that does Bluetooth data exchange with your device, which means wireless communication, which is basically serial communication in wireless form, which also you learn in 8051. It has a serial port, right? So that is one example. Another example, the weighing scale, the speedometer, the digital instrument panel, which is there in bikes and cars today, all of them do fancy things from a layman's point of view. But you're not a layman. You want to learn engineering. You want to become an embedded system developer. You want to see things the right way. All of those fancy things are eventually programs which are executed by the microcontroller inside. Okay? Now, where did the idea of a microcontroller come from? Originally, a microprocessor was made. I'm taking you way back in 1970s, Intel 8085. So a processor executes programs. Okay? All the fancy things that we do, like I said, are eventually execution of some program. So that's what your processor does. It doesn't store programs. Programs are stored in the memory. So a processor cannot work all by itself. It needs connection with memory. Now when you say memory, lots of components come in your mind: hard disk, floppy, CD, DVD, pen drive, etc. They are all secondary memory. Primary memory, the original form of memory, was RAM and ROM. So when you're learning a basic microprocessor or a basic microcontroller like 8051, your concept of memory is RAM and ROM. There is a difference between RAM and ROM. RAM is random access memory. It's a writable form of memory, so you can write, read, change it again, read, change it again as many times as you want. It is volatile, which means the moment you switch off power supply, the information is gone. You turn on power supply back, or there's nothing remaining. Now whatever you store, you can read that back. Are you clear? So it's writable, but it's volatile. Volatile because it loses data when you switch off the power supply. The other one is ROM. ROM is permanent, non-volatile in technical form, which means you remove power supply, it will still hold its information. So the good thing is that it holds information even if there is no power, but the bad thing is you cannot change the information. That information is permanent. Of course, that was the original form of ROM. Then came PROM, then came EEPROM, then came EEPROM, then came flash ROM, the kind of memory that you use in pen drives. Anyway, but still it is ROM. A pen drive is there in your pocket. You don't lose the information. There is no power supply there, but you don't lose information. So it is still ROM, but it's the modern form of ROM where writing happens. Again, those modern forms are in today's era. When you're learning 8051, you have to know you're learning something that was made in 1970s. So you have to keep those things in mind at least when you start, till you get a good handle on it, and then you incorporate modern ideas into it. Are you clear? Otherwise, if you just relate everything that I'm saying to the modern world, there is a gap of 45 years of technology that is between the two. You're going on a tangent, you're putting wrong ideas into it. So first, get accustomed to what the original system was. Okay? So when you say memory, there is ROM, there is RAM. What did I say? The purpose of your processor is to execute programs. Where are those programs stored? In the memory. A program is a set of instructions. Any program is a set of instructions. Every instruction is first fetched from the memory, decoded so that the processor can understand what does that binary pattern mean, and then execute. Like this, one by one, it executes instructions, and that's how your programs run. Okay, I'm just giving you a brief idea. Now, in the memory, other than programs, we also store data. You got to get this clear. There are two things which are stored in a computer's memory: programs and data. Are we absolutely clear? Okay? I'm not mincing words, I'm not trying to speak a confusing language, I'm being crystal clear here. Every file which is there in your computer's memory is either a program or data. To give you examples, WhatsApp is a program. The messages of WhatsApp are the data. Instagram is a program. The images that you see are the data. Song player is a program. Songs are the data. Microsoft Word is a program. Those documents that you create using Word are data, and so on. I can go on the whole day. I think you got my point, right? In this remote control that controls the AC, there is a program that runs this remote control. Tell me, what is the logic of that program? What does the program have to do? Let's have a simple discussion. First of all, identify which key is pressed. So there's a keyboard program. Are you clear? Which you will learn when you learn 8051 in full detail. I'll make a special course on it for keyboard programming. Anyway, there is an LCD program, because what you press on the keyboard, you shouldn't be kept guessing what you pressed last. There should be a display that tells you what you pressed. It echoes your information back on the screen. So there's an LCD program. There's a serial communication program that sends whatever information you sent over there to the receiver. The receiver will take the appropriate action, right? So these are programs. Those programs are stored in the memory, not inside the processor. They are stored in the memory. Are you clear? What else is stored in the memory? Data. What is data over here? Songs? No. Movies? No. The temperature that you set, which you can change, correct? You may not be able to see it, but you are smart enough to know what these buttons are. So the up and down arrow button, come on, that's the temperature increase and decrease, right? There are mode buttons to see which mode your AC is going to work in. There are fan speed buttons, whether you want low, high, medium, or automatic, which is what I always keep at. Anyway, when the computer can do the thinking, why should we do? Anyway, so those mode selection is the data, fan speed selection is the data, and of course, temperature is the data. There are even timer functions over here where you can set the AC to be on at this time and then automatically go off in the middle of night at this time, so that it doesn't become too cold. So those starting times and ending times are the data. The timer is a program, but those times are the data. You understand the difference between data and programs? Even the data is stored in the memory, so are the programs. Are we clear? They are not stored in the processor, they are stored in the memory. Other than processor and memory, there is a third section to build a computer, which is the I/O section. Now this is something which I don't need to say anything about. Everybody knows what is I/O. I/O stands for input and output devices. Come on, your keyboard is an input device. Your mouse is an input device. Your trackpad is an input device. Your monitor, of course, your speaker, they are output devices. Your printer is an output device. You understand what are input-output devices? Do the input-output devices execute our programs? No. If I want to add two numbers, I give those two numbers using the keyboard, but the keyboard doesn't add them. The keyboard sends the numbers, stores them in the memory, processor takes the numbers from the memory, processor will do the addition. Are you clear? The keyboard was used just to give inputs. Similarly, monitor. Is monitor creating the images? No. Monitor is displaying the images. The processing of the image is happening by the processor. The processor will process it, give it to the monitor, monitor will simply display the image. Printer will simply print the file, but it's not creating the file to be printed. That's created by the processor. So all the action takes place here. The main component of a computer is the processor. That's why we learn it so much, but it can't work alone. It needs memory, both types of memories, RAM and ROM. It needs I/O. I'm going to go one step deeper. When you say I/O, I/O mainly consists of ports. You know, on your phone, on your computer, there are ports in which you connect things, right? On your computer, there is a monitor port, there is a keyboard port, there is a mouse port to which you connect all of them. Today, most of them have become USB ports, Universal Serial Bus ports. But anyway, back in the day when it all started, they all had different kinds of VGA port, there's a proper keyboard port, there's a proper printer port dedicated only for the printer, and so on. So my point is, you have these IO ports on which you connect IO devices. To build a computer, you need your processor, you need RAM, ROM, you need IO ports, you need something called timers to run time delay applications. Simplest example I showed you, something so basic like a remote control also needs timer functions. Various operations need timer functions. Your song player tells you how many seconds have elapsed and how many seconds are remaining. Your walking tracker, of course, needs your time. You're doing a 1 hour walk, it's going to show you your time, it's going to calculate the distance and blah, 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 your speed. So you know what I'm talking about. So there are something called timers, which is there in our subject, and I'll be teaching you in this particular course itself. But anyway, so there are timers that you need IO ports, and you need all of this. Fine. So let's put all of them. Of course, now you're not going to just keep all of them next to each other. You're going to connect them. So to connect them, you need something called buses. What I've shown over here and here are called buses. What is a bus? A set of lines grouped together is called a bus. There are various types of buses: address bus, data bus, control bus. You can guess the operation by the name itself. Address bus gives the address at which you want to do the operation. Data bus carries the most important thing, the data that you want to transfer. And the control bus decides whether the data will be sent or taken, which in technical terms is called a read when the processor takes the data, and write when the processor sends the data. These things you will learn in detail as the subject proceeds ahead. Anyway, so you'll need all these components connected with all of these buses. To do all that, you need space. You need a big board called the motherboard, which you've seen in a computer, where you see your processor, you see all the components, and you see those wires which are printed on the motherboard. It's a PCB, printed circuit board. I'm sure you know that, right? When you see the backside also, you can see the whole circuit design. Anyway, so you need all of those components with a big motherboard, then you make a perfect computer. Fine. Now to put all of that, you need space. Correct? Simple common sense. To put all of these components, connect them together. I've still not even told about power supply and the decoding circuits and all. I've told things which you'll simply understand from the basic idea. But there are more things to it also. So you need all of those connected on the motherboard. For that, you need a lot of space. Where do you have this kind of space? In a computer. In a computer, you have that big CPU. If it's a desktop, you have a big CPU which has tremendous real estate space where you can put a big motherboard and make a lavish computer with too many functions. Great. You also have this kind of space in probably a laptop, right? The backside behind the keyboard, that whole panel inside is space for your motherboard. You have the space probably in a tablet, probably in a phone, but devices are much smaller than that. Something like this remote control cannot afford the space for such a big motherboard. Something like a car remote control, if my car keys are here, okay, great, my cameraman was parking my car, he has my keys, yeah, there you go. Does this do programming? Come on, of course it does. Of course, there's no magic, right? I press the lock button, the car locks, I press the unlock button, the car unlocks. So what should I do? Should I go to the terrace of my building, point at all the cars, and press the unlock button, let all cars unlock? I'll decide which car I want to drive. No, it doesn't work like that. That means, other than locking and unlocking, it also sends a code which my receiving car matches. That code is the identifier. That's what allows me to enter my car, correct? Now, that code will not be sent directly, because if it's sent directly, then somebody can hack it, start my car, right? You've seen movies. It happens at least in movies. So the code will be sent in an encrypted form, which only my car knows how to decrypt. And that's how it will recognize that I'm sending the signal, and that's when it will unlock. Are you understanding? Now, this is not rocket science. You don't need to read big textbooks for this. This is just simple, straightforward thinking. You become an engineer the day you can start thinking like an engineer, not when you get your degree. That one sudden day will not transform you into an engineer. When you start looking at the world like an engineer does and understand the science behind it, that's what these subjects do. They equip you with the knowledge so that you can see what is not visible clearly, the matrix. Anyway, that's just a joke, but anyway. Yeah, I keep saying we live in a matrix. Now, jokes apart. So, does this require programming? Yeah, the first program is to know which key is pressed, second program to send that information serially, third program to do the encryption of the identifier and send that serially. Are you understanding? So for that, this also requires a processor. Since there's program, since there's data, the code plus the buttons that I'm pressing, that's the data. So there is data, there is program to store that. I will need memory, I will need I/O because there is an input port which takes these buttons, there is an output port that sends the signal. So I will practically need all of these components. Maybe I don't need the timer, but I'll need everything else. Do I have space for a motherboard over here? There are smaller devices also. I can go on. I think you got my point. Devices are really small. Pacemakers that you put inside a person's heart. What a beautiful invention. We feel proud calling ourselves engineers. We are the ones who made these things and so many which you will take forward, the new generation. You put a pacemaker, it detects the pulse, heart rate of the heart, and if it notices it's gone beyond a particular level, it's gone too low, it gives an electrical spark, a jolt, so that the heart wakes up. Right? If a person notices it around you, they will do it. But if this happens during the sleep and no one's noticing, at least it should be able to revive the heart by giving that jolt. So it's an embedded system. It also has a program to do all this detection. It requires memory and blah jazz, the whole thing. But there is no space for a motherboard in it. It's a very small device. And like this, there are tiny, beautiful devices doing wonderful things in the world, but there's no space for a motherboard in them. But what you would want is somehow, if you get all of these functions in one single chip. Wouldn't that be awesome? A single chip which has a processor also, RAM also, ROM also, I/O ports also, timers also, and many such things which are useful to build a system. Wouldn't that give you a very compact computer system? That is what is a microcontroller. Do you understand the difference between a 𝗵𝗶 and a 𝗕𝗵C? This is your microprocessor. A microprocessor is just a processor. A microcontroller is everything put together in one chip, the entire system built on one chip. So what is the basic advantage of using a microcontroller? Gives you a compact system. Is it as powerful as your computer? No. Does it need to be? No. The pacemaker doesn't have to play songs. It doesn't have to print things. It doesn't have to shoot emails. It doesn't have to do anything. It just has to take care of the heart. This AC remote control just has to switch off the AC, set the mode and do the time functions, nothing else. It doesn't need an OS. There is no Android or iOS inside. It needs a basic program. It doesn't need that kind of processing which a Core i9 or the M1 chip can do. But it still has to do programs in the most compact way. Like I said when I started, everywhere you don't need cutting edge processing. Very many places you need basic processing but in a simple, compact and cost effective way. You understand the cost of building a whole circuit on a motherboard with all those separate chips is tremendously high as compared to buying just one chip. The power consumption is low, the heating is low, the space required is so much smaller and so on. Those are all the benefits of using a microcontroller. So that is why we use it. So where do you use microprocessors and where do you use microcontrollers? In computers, in tablets, in phones, where you require tremendous level of processing, you use microprocessors. In appliances, you use microcontrollers. Appliances which have a dedicated task to run, you use a microcontroller because it does the job in a single chip. Now, what are sold more in the world? Microprocessors or microcontrollers? Of course, microcontrollers. There is no comparison. Look around yourself. How many computers do you have at home? One, maybe two, three phones, right? Maybe one or maybe two tablets. That's it. Now tell me how many appliances you have. You'll be amazed. You'll be amazed. Your TV is an appliance. It has a microcontroller. Your TV's remote has a microcontroller. Your set-top box remote, your video player's remote, your music system, its remote, all your music appliances, your fridge, your washing machine. I can go on. You are living in a land of microcontrollers. There's so many. I will go one step deeper. Your computer, of course, has your microprocessor that runs the whole computer. But in your computer, there are so many appliances. Your computer has a printer. The printer has a microcontroller. Your computer has a keyboard. The keyboard has a microcontroller which identifies which key is pressed. The main computer is not going to identify which key is pressed. That's the job of the microcontroller which is attached on the keyboard. Your mouse has a microcontroller which identifies the XY coordinates and the keys save pressed, and so on. So in your computer also, though you have one big microprocessor, you have several microcontrollers assisting it, and so on. So now immediately I hope you understand how important it is for an engineer to learn microcontrollers. They can be used for smallest applications to the biggest ones, to fancy ones, those light decorations that we see which are a part of every function now. Defense system, radar tracking, RFID sensors, all of those toll sensors, they all use microcontrollers. That's why we're learning it. So my goal of this particular lecture was to make you understand what a microcontroller is and how different and useful it is as compared to a microprocessor. We are not trying to build the most powerful system. We are trying to build the most efficient system, cost efficient, space efficient, power consumption efficient. Are you clear? So that's where microcontrollers are. Your calculator is a microcontroller. You buy your calculator when you start engineering. You hope that it lasts all the way till the time your engineering is over. It uses a microcontroller inside. Anyway. So that was our introduction. In the next lecture, I'm going to tell you things about 8051.